Okay, next test. Direct comparison test. That just states that if you have a series right here, a sub n, and it has no negative terms, then this series, a sub n, will converge. If you can find a series, and we'll call it c sub n, where the terms of my a sub n are less than or equal to the terms of c sub n for all n. What this means is if you have a series and you can find one that's bigger, that's always bigger than the one you're starting with, and if this one that is bigger converges, then this one which is underneath it at all times also has to converge. And same thing goes for a divergent series. If you have a series and you're trying to prove if it's convergent or divergent, and you find another one where the terms are greater or equal to this one, then you will have a divergent series. So in other words, if this one here is always bigger than this one, or on top of it, above it, and you know this one diverges, then this one has to diverge also because it's bigger than this divergent series. So I know that's really confusing, so I'm going to go through it one more time. If you have some series and you're trying to prove if it converges or diverges, and you can find another series that is bigger than it, and you can prove that this bigger series actually converges, then this other series here that you have, which is smaller than the convergent one you found, it will also converge because it's smaller than it. It's underneath a converging series, so it will converge. And also, if you have a series and you can find another series that's smaller than this one, and if this one diverges and it's smaller, this one has to diverge because it's bigger than the divergent series. Okay, here's a picture to hopefully help clear things up if you're still confused. Here's a sub n. This is a series in red that you're trying to prove whether it's convergent or divergent. So if you can find another series, B we'll call it, that's bigger than a sub n, and if b sub n converges, then this series underneath it must also converge. And vice versa, if you are given b sub n and you are trying to prove if b sub n is convergent or divergent, and you find another series that's smaller than it, and if this series here does not converge, it goes on forever and never actually comes to a finite number, then this one that is larger than it must also diverge. All right, so let's just try an example. So here's the series, and we need to determine if the series converges or diverges using the direct comparison test. Okay, so if you look at our original function or series that we're trying to prove convergence or divergence on, I'm just going to look now at the denominator. The denominator of that thing is n to the third plus 1. And hopefully it makes sense. N to the third plus 1 is always going to be bigger than just plain old n to the third. So now we know that since this denominator is always bigger than this denominator, this will be smaller than this. So we found something smaller everywhere. So now if I multiply both sides by n, this is still going to always be smaller than this one. Then I'm just going to reduce this one to 1 over n squared. So basically what's going to happen here is I'm going to take my series right here and do a direct comparison with this one, knowing that this one is always going to be larger than the one I started with. All right, and now I'm going to look at this one I picked that's always bigger than the one that I have. And I know it's a p-series, and so the p-value is larger than 1. So this series that I picked is convergent. So by the comparison test, since this one is smaller than a convergent series, this one is also convergent. Okay, here is another example. So we're going to determine if this series converges or diverges by the direct comparison test. So write down this example and we'll work it out. Okay, so this one's very similar to the last one. If we look at the denominator of our series, it's this right here. And this is always going to be greater than n to the third, because n to the thirds here are equal, and then all I do is I add on values. So this side here will always be larger than this side. So because this is bigger than this, when I divide by them, this right here now becomes smaller than this. And this is the series we're trying to work on. So we have found another series that is always going to be larger than the one we have. So if we can prove this one converges, then this smaller one must also converge. So the one that we picked here is a p-series, and the p-value is 3, so it is convergent. Therefore, since our larger series converges, our smaller one that's always underneath it must also be convergent. Okay, here's one last example. We're going to use the direct comparison test to determine the convergence or divergence of this series right here. And so I need to find a function to compare it to. Well, I know that the natural log of n is smaller than or equal to n when n is 2 or greater. And if you need to, just picture the graph of this and then picture the graph of this, and it'll be clear that y equals x is bigger than the natural log of x. So then if I reciprocate them, I know that this is going to be larger than this one for n greater than 2. So now I have a function that is smaller than the one I'm starting out with. So I'm going to test for its convergence, and I know that's the harmonic series. So I know that this series here is harmonic, and so it's divergent. So since my function I started with is larger than this divergent series, 1 over n, our original function also has to be divergent.